Okay, it started?
Yeah.
Okay, good. Well, okay, I'm going to talk about the twist defect. I realized that when I prepare for the slides that this title actually conveys too much information at once. There's defects, there's twist defects of global symmetries, and there are generalized global symmetries. So after the second thought, I decided to start by unpacking this title step by step so I don't get lost. Now, defects in quantum field theories have a very long history of research. One physical motivation why people care about defects is that they are probe particles that are infinitely heavy and static in the many-body systems. The heavy particle could interact with the light particles from the surrounding quantum field series, and more importantly, they can have their own RG flow, even when the environment is already at its fixed point. Now, in the family of the defect, there's a very special class where you can deform the shape of your defect continuously without affecting any physical observables. And these defects are topological defects. In recent years, people have realized that topological defects provide an extremely useful and a generalized framework to study symmetries in the quantum field series. Now, for an ordinary global symmetry, as you can find in your favorite textbook, they are codimension 1 topological defects associated with group elements. Now, the generalization goes into two directions. First can be have higher codimensions, and that leads to what is known as higher form symmetries. Or their fusion rule can be more complicated than that of the group, and that leads to the categorical symmetry. I want to set up the convention here that whenever I mention the symmetry defect in the rest of this talk, I always refer to the codimension 1 topological defects. That is, the fusion rule does not necessarily have to be group-like. So in other words, I'm only generalizing in one direction in this more modentation of symmetries. Is everybody fine? Okay, good. Okay, symmetry defects are interesting, but they're not the hero of this talk. Today, I'm going to talk to you about another very special class of defects that are the boundary of the codimension 1 symmetry defects. So, by definition, they are the boundary of the codimension 1 operator, and I want to highlight the difference here. So, symmetry defects, they are codimension 1, and they are topological, while the twist defects, they are codimension 2, and they are almost always not topological. People already know the twist defect very well in the case of 1+1D quantum field series. They have some other name. For example, the twisted field, which by the state operator correspondence are mapped to the spectrum of a twisted Hilbert space. Or if you are more familiar with the string theory, those twist defects that live at the end point of the symmetry defect of the fermion parity operator are also known as a remote field. One interesting property of these codimension 2 twist defects are that they are almost always non-trivial. They are non-trivial as long as their associated symmetry defect act faithfully on local operators of the quantum field theory. That is because we can always identify the locus of our twist defect by starting the branch cut in the correlation functions. So in other words, they are a robust way to engineer some non-trivial, maybe conformal, maybe not conformal defect in a possibly strongly coupled QFTs. Now, people have done a lot of studies about this twist defect, primarily because they are related to the Brook factory, where you calculate the entanglement entropy of the field theory or the lattice model. Here, I'm providing a highly incomplete list of references. If anyone in the audience who have wrote a paper about subject that I missed, I'm sorry, please let me know. But today, I'm going to tell you another motivation why people, or I should say, why experimentalists should care about the twist defect. Now, before I jump into the example, is there any questions about the convention, about what is twist defect and what are the symmetry defects? Any question? No? Okay, good. No, right.
Maybe I'll ask a question. So
yeah, sure.
for the entanglement entropy, what is the symmetry defect for which the twist defect is the
Right. So in order to calculate the entanglement entropy, you would have to implement some branch cut. and you can glue the theory on different sheet and do your density matrices. So one trick to make that symmetry rich is that you can insert such a twist defect at the bridge cut point. And that would introduce some new structures in your entanglement entropy.
And this is a kind of charge result.
Yeah, exactly.
But you're not saying entanglement entropy itself as the interpretation.
Well, true. Right. Okay. Imagine that you are an experimentalist, or some people are indeed experimentalists.
They have both, yeah.
And you want to work with, for example, with a sheet of graphene in your next lab, but your equipment is so crap that you end up with imperfection somehow in your lattice sheet. And these imperfections can either be, if you work with 2+1D, can either be disclinations or dislocations, or if you are working with higher dimensional lattices in 3+1D, that could be some more complicated structure. One physical way of thinking these crystalline defects or lattice imperfections, for example, the dislocation, is that you can identify an array of atoms in your perfect lattice, and you can remove them, and by gluing the atoms on the two sides of the array, you can create, at the end point, a dislocation defect. And a similar construction also holds for the disclination defect. Now, the question is, what do these defects become in the infrared, maybe in a continuum quantum field theory description of your lattice sample? And the answer is less trivial than what you might thought. So to show that, I'm going to talk about a specific example where we have a free Hamiltonian for the fermionic creation and annihilation operators on each lattice side, coupled through some Pauli matrices. And on the on-site lattice term, there is a on-site term controlled by the parameter m. But the discussion here is completely covered for general. I'm showing you the free model because it's easy and we can work out everything exactly. So if you look at this UV model of your lattice, you would realize the global symmetry are such that, for example, first, there is a global symmetry that is U1. And for the spatial symmetry, you actually get a discrete lattice translation that is Z times Z, and also a lattice rotation, which is order M, that depend on the shape of your lattice. For example, M equals to 4 for a square lattice, and equal to 3 and equal to 6 for other types. Now, that's a different model that as opposed to what you have in the continuum. For this particular model, at the quantum critical point with the specific values of M, you can end up with either one or two or many flavors of Dirac fermions. The theory at IR has a dramatically different symmetries. The flavor symmetry can be extended or remain the same depending on how many flavors of Dirac fermion you end up with. That is something dependent on the band structure. So you have to do the Fourier transformation, do the math. Now the spatial symmetry for sure get extended, and for these particular quantum critical points, it is get extended to the 2+1D conformal group. And there exists a map which we denoted by rho between the UV system and the IR system. The map rho, of course, act on the operators. For example, the parameter m in the non-lattice interaction in the Hamiltonian are associated with the mass term for the Dirac fermions in the infrared. When it comes to the symmetry, however, the rho, the map, looks a little bit involved for the lattice translation and lattice rotation. And that's what I'm going to work out. Okay, it's not really that involved, at least for the lattice translation, because the Dirac horns are with each Dirac horn are with their own momentum in the Fourier zone, and therefore acting on a translation by certain vector in the spin lattice in the lattice length units. You get the IR field, the Dirac fermion field, transferred with respect to translation, Lorentz translation, and also picks up a phase determined by the core momentum in the beta structure. The lattice rotation is a little bit more involved. In principle, you can end up with a UN phase that alternates different flavors of Dirac fermions. you can always find a base where you can diagonalize this unitary transformation, and the eigenvalue is associated with a set of topological quantum numbers, that is SI. Now, one easy conclusion that you can find is that if you are at the lattice level, you have a order n bosonic rotation operator. Those topological quantum number S has to be a half integer to satisfy the spin statistic of the Dirac fermion in the infrared. So they are non-trivial. And then now, if we consider those lattice imperfections, for example, the dislocation and disclination as localized flux for those lattice translation and the lattice rotation, we would end up with a conclusion that the correct way to describe these models in the infrared are that first, you have to implement a curved spacetime that implement the Lorentz translation and the Lorentz rotation. And meanwhile, you also have to consider a flux of the global symmetry in your infrared model. And they are what we call the eminent flux that is induced by the non-trivial map between the UV symmetry and IR symmetry. And these flux are exactly what I have been talking about a few slides ago. They implement what is known as the U1 twist defect. So first of all, they're codimension 2. They are a line defect that extend in the time direction. And the second, the field picks up a global symmetry transformation upon winding around it. So there are the twist defects. And this is a phenomenon. This road leads to a mixture of the UV lattice spatial symmetry with our global symmetry. Is a phenomenon known as the eminent symmetries. Yeah, please.
Sorry, can you explain the difference between eminent symmetry and emergent symmetries?
Right, very good question. When people talk about emergent symmetry, they talk about the approximate symmetry that could show up in a low energy vector series. In that case, the symmetry is not always exact. You can introduce possibly some UV perturbations that could destroy the symmetry. Here, by eminent symmetry, or even though I'm not showing that explicitly in these slides, they are induced by the UV lattice translation and the lattice rotation. Those UV spatial symmetries are mixed with the global symmetries in the IR. And in that sense, this part of symmetry is exact from the UV to the IR. There's no perturbation you can introduce to destroy them. Okay, so that's why people invented a different term for eminent symmetry. Yeah, please.
Sorry, are you going to talk about this? But in general, how do you match anomalies?
Well, we did in our paper, but that would be a digression. I want this discussion here to serve as a motivation why you should care about twist defect, because you have to deal with them if you have these lattice imperfections. And the flux, how large the twist is really dependent on this non-trivial map. That's the part that is technically more involved, but I'm not going to discuss that. Okay. Any other question? Good.
Sorry, so S naught, what are these S parameters there?
Right. So the S parameters are
something intrinsic to the UV lattice model?
Yes, it's intrinsic to the UV lattice model. And depending on the lattice model, they are subject to different selection rules. For example, if the lattice rotation in your UV model is of order n, is a bosonic operator, they have to be the half integers in order for the Dirac fermion field to satisfy the spin selection rule.
So in the UV, the like rotation group is extended by the U1. Is that what's happening? That's why we have that UIJ there.
In the UV, rotation symmetry is extended.
You have that the rotation group is acting. That U phase. Right. Is that part of a flavor symmetry of the UV model?
Right. So it's a part of flavor symmetry in the IR model. There's no such a thing. There's no UV matrix in the UV. Okay. I should explain more because here I have an upscript that depends on which the center of the rotation you are taking. But there are two different types. You can take the rotation at the blockade center or the vertex center. So, but okay, I should apologize. I'm not getting into the detail of everything. I just want to serve as a motivation why lattice people, lattice experimentalists, should care about monodromy defect or twist defect. So that's one scenario that you would probably end up in your lab. And the correct model, actually, it turns out in the IR, you have to consider a monodromy line defect a twist line defect that is intensive in the time direction. And for this free Dirac fermion model that is easy to work out, here I'm just saying that there's a standard trick by mapping the system to ADS, which is really an overkill. So again, I'm not going to get into detail, but eventually it's just a free model. You can just solve the equation of motion and find out everything exactly. So the presence of the defect leads to some physical consequence. In a bulk where you are away from the defect, you end up with a free Dirac fermion, the dimension of which is fixed by the dimension counting, which is 3/2. As you bring the bulk operator psi close to the twist defect, which is a localized point in space, conformal symmetry, first of all, is broken. And the bulk spinner is decomposed into a family of defect spinners that has a different dimension than that in the bulk, which is 3/2. And in particular, the dimension of the defect spinner takes the dimension that is dependent on the orbital momentum, which when you do the mode expansion is dependent on this half integers that denoted by S. So the point that I want to make here is that the presence of a twist defect makes two major differences in the physics. First of all, the twist defect can preserve a residue conformal groove to your bulk conformal symmetry at a long distance. And therefore, the operators living on the twist defect shall be characterized by the quantum numbers of the residue conformal symmetry. And the second, there actually exists two different RG fixed points for the twist defect corresponding to the solution where the lowest lying, the spinner component with the lowest lying orbital angular momentum with equals to -1/2, taking a plus sign in the dimension or a minus sign in the dimension. Okay, that is a little bit abstract. If I'm from experiment side, I would complain, okay, this is mathematical nonsense. How do I even measure? How do I even tell which fixed point my twist defect, my lattice imperfection lives in? Well, the answer is that you can consider about some physical observables in the bulk. And that's what we calculated. Two useful physical observables to consider are the U1 current associated with the global symmetry and the stress energy tensor, which is essentially the energy densities in the bulk. And then these one-point functions are strongly constrained by the residue conformal symmetry. In particular, their form are completely fixed up to an overall coefficient. And for IR stable fixed point characterized by the plus sign here, and the multi-critical fixed point characterized by the minus sign here, they lead to different curves of this one-point function coefficient as a function of the U1 flux alpha. So this is the direction of the RG flow. You can, if you live at the multi-critical fixed point, you can always turning on a local perturbation, which is the quadratic form of the fermion operator that takes you on the RG flow to the stable fixed point denoted by the blue curve in this picture. Now I want to remind you how similar this picture is to the phases, to the energies of a particle in the ring in the quantum mechanical model.
Sorry, can I just try to understand the picture a little better? So the fixed point is at particular values of alpha? Sorry, maybe I was not following well.
So yeah, okay, so that's my bad. I should explain it more. So for each values of the flux that you inserted that is induced by these lattice imperfections, it corresponds to two different RG fixed point for the defect spinners. And then two fixed points are distinguished by looking at the spinner component has the orbital angular momentum.
So for each alpha, there are two fixed points.
Yeah, exactly.
And do they ever merge at some particular?
That's what I'm going to say in the next slides.
I had a question. So
Yeah.
here you're kind of forgetting about dislocations in a sense and just thinking about the U1.
Oh yeah. Okay.
In the original model, could you get any alphas, or it was just kind of probably a handful of alphas?
Okay. My bad. So first of all, here I'm considering the dislocation for particular, and the space-time background is not does not have any curvature background, does not have any conical background singularity. In general, for the disclination, you will have to consider about certain conical singularity at the location of a defect. That's what we did. We did in our paper. The result has to be modified slightly. But for the interest of the twist defect itself, here I'm only showing you the case where the background is not conical. But what was the second part of the question? Can you repeat it?
So this slide gives me the impression that you're going to do free Dirac with a defect for UV1, okay, which isn't quite what you were doing on the lattice before. So on the lattice, I understand you're not doing disclinations, but dislocations mapped to some things in the IR that included a one flux.
With the flux determined by the Dirac co-momentum as well as those logical quantum numbers, which I did not explain. In general, that's a model dependent thing. So how much flux is really depend on what is the UV lattice model you're working with. So here I'm considering a more general setup. I'm trying to play with all possible values of alpha. Okay, yeah, please.
So what is alpha in the microscopic model? Is like the excess angle or something?
No. So this is something you cannot find at the lattice model. So in the UV lattice model, all you have is some lattice imperfection induced by some vacancies or some very strange atoms that has a different valence bond with respect to others. It is only when you go to the IR description that you have to consider the non-trivial map that maps the translation and that lattice rotations to a non-trivial element of the IR symmetry. So that's in some sense something only observable in the IR. Does that answer your question? Okay, good. Okay. Okay, so we were saying that there are two different possible fixed points of the twist defect, and they are, one of them is multi-critical and one of them is IR stable, and there is specific perturbation that you can turn on that takes you from this multi-critical one to the IR stable one. And if you are more practical and you want to know what are the physical consequences of having such a defect, here I'm suggesting that you probably should look at the U1 current and the stress unit tensor, which the response, they actually, as a function of the alpha parameter, had a different response for the multi-critical fixed point and IR stable fixed point, and the RG flow takes you goes in this way. I want to remind you how similar this is as to a quantum mechanical model of a particle on the ring, where you have the magnetic flux, also, let's say, for example, parameterized by alpha going through the center of the flux, going through the center of the circle. In that model, at a particular alpha, alpha equal to 1/2, there will be a level crossing of the ground state, as indicated by the anomaly. In this case, however, we are looking at a many-body system. And again, at alpha equal to 1/2, we found a crossover of the defect fixed point. That's something dramatically different. And the interesting thing is that at the fixed point, we identified an exact defect conformal manifold. The parameter that takes you from the UV fixed point to the IR fixed point now becomes a exact conformal parameter that you can slide along the direction of the conformal manifold. And it happens that the CJ coefficient is the Zamolodchikov metric, the Zamolodchikov distance of this finite conformal manifold. And this actually leads to some important implications for experiments. With the presence of an exact marginal parameter in your setup, you actually cannot end up with a unique IR limit, right? Because now, as you get closer to the crossover point between the fixed point, the closer you get, the larger the finite size effector are. And eventually, when you are at the flux equal to 1/2 point, where you have an exact defect conformal manifold, now the IR prediction of your theory can be any point along this line, which is the characterization of the defect conformal manifold. And that is indeed what we found from numerical simulations. So here, by flag, we are inserting some external flux on top of a perfect lattice. And by the blue curve and the white curve, we are exerting the same amount of external flux on top of some lattice imperfections. So there are 2 points I want to remind you about these two figures. Well, first of all, the blue curve and the white curve which are the case you have some lattice imperfections, they're horizontally shifted. And the amount of shift, that's something we can verify and indeed check. They are supposed to match the theoretical prediction that we get from the UV lattice model about those topological quantum numbers and the Dirac momentum, and that is indeed the case. As you get closer to a certain point where the total flux equal to 1/2, you would have found somehow your numerics is going to break down. So you end up with some result that converge very slowly. That's not your bad, actually. It's not that you are doing your numerical techniques very bad. It is because of this existence of the exact defect conformal manifold that you always cannot end up with a unique error limit. So that's a simple numerical verification of the picture that I told you about. And that's one interesting physics phenomena regarding with this the U1 twist defect in the free Dirac fermion. Now,
Can you go back one slide? Sorry.
Yeah, please.
I want to understand this arrow at the bottom there, that when you have a defect conformal manifold, you
Yes.
expect very large finite size effects. Could you just expand on that a little bit? Like, why should we
Right.
expect this?
Right. Well, to consider any finite size effect, in principle, you have to consider all the irrelevant perturbations to your theory. You can write down these perturbations with certain coefficient that is determined by the UV scale with, let's say, from order 1 coefficient. But they are all suppressed as they are over the UV scale, which is usually a very large quantity. It only becomes a major concern when they have the dimension that is close to marginality, and then the other parameters are no longer suppressed by the UV scale anymore, and there are some order 1 concern that you should worry about. That answer your question?
Why does the conformal manifold matter? I mean, what you just said is generally true, right?
What?
Why does the existence of a conformal manifold matter for that argument?
Well, the conformal manifold meaning that there is always some perturbation you can write down, which is of order 1 in your final result, in your IR predictions, in the physical observables that you get.
I mean, these are meant to be exactly marginal. These are exactly marginal operators.
Yeah, they are exactly marginal.
I guess you're saying there's finite size effects right next to 1/2 because you have nearly marginal.
Oh, yeah, okay.
Yeah.
True. Let's say you have some lattice imperfection with particular set of topological quantum numbers and the Dirac momentum that end up with a flux that is extremely close to 1/2. Okay, it could happen for the specific numbers you had in mind, and then you would end up with extremely large, depending on how close you are going to get from 1/2, an extremely large finite size effect due to this close to marginal parameter you had in your theory. And at alpha equal to 1/2, that's where exactly the thing got out of control. Now you have the exact marginal parameter. Okay. All right. Okay. So far, I've been talking about some simple physical implications and maybe applications for the twist defect in the free Dirac fermion.
So can I just go back to this one more time?
Yeah.
Do you really expect this in a real experimental setup to be protected? I mean, is it really
Protected.
equals 1/2 exactly marginal operators? I mean, I thought generically we don't expect exactly marginal operators to survive in a setup that's not
Well,
special.
this kind of defect exists if you want to preserve the conformal symmetry. Well, in principle, let's say this is your bulk theory, and you want to consider more relativistic case where, let's say, you have some 4 fermion interactions, etc. In that case, whereas the bulk theory is not conformal and the defect theory as well is not conformal, then I think it's not making any sense to talk about conformal manifold at all. But if you do want to preserve conformal symmetry and you are looking at this critical point described by the free Dirac fermion, and you want your lattice defect, your IR defect to preserve the conformal symmetry as well, then yes, this one is what you would eventually find. yeah, I realized this could be a very too strong constraint to consider about conformal symmetry over and over again. But again, we did some numerical simulation in Monte Carlo. Probably we should try more, but this is indeed what we found. The numerics are guaranteed to break down at a certain regime, no matter how large we did. It just converts slowly, more and more slowly as we get close to the total path. Okay, right. Okay, so far I've been talking about the twist defect in the free Dirac fermion. Well, the same exercise could be carried out also for a free Dirac boson. Everything is similar. You can just try to find out the defect operators that have a different dimension and try to characterize them by the both functions of the current and the stress energy tensor. And the curve is shown in the picture. One funny fact is that if you want to consider some n equal to 2 supersymmetric chiral multiplet, and you want to preserve the 1,1 supersymmetry along the twist defect, you would have found that the IR stable fixed point of the free boson are actually locked, tied with or associated with the multi-critical fixed point of the fermionic sector. And by preserving the supersymmetry and advancedly dial the flux from 0 to 1, you actually do not end up with the same trivial defect that you start with. This holonomy of the fixed point somehow lead to an extra qubit localized at the defect location, as indicated by the defect entropy function, which is just a funny fact that I want to entertain you with. Okay, so far, I'm leaving you the impression that these twist defects in free boson, free complex boson, or free Dirac fermion are something that can be solved, and they lead to some experimental implications. I think it's a natural question, at least for me. It's my curiosity. Is it possible, or does it make sense to define the twist defect in gauge series as well? That's probably the next thing we want to do if you want to study some supersymmetric series. And that's what I'm going to talk about in the next 20 minutes. So before that, is there any questions about the lattice imperfection and the free Dirac fermion case? Okay, everybody so far, so good. All right, thank you. Okay, so the first question that you might have in your mind is that, okay, what is the symmetry of a gauge theory? Let's consider the simply possible case that everybody know from the undergraduate, that is essentially the Maxwell theory, that is the U1 gauge theory in 3+1D. If you look at the equation of motion, which is Maxwell equation, you might notice, okay, there is a natural symmetry that is a charge conjugation, which set the electric field and magnetic field also to the minus of themselves. But there's actually, in some sense, more elementary symmetry that is implemented by this transformation rule, and that is the electromagnetic duality. And indeed, by acting this duality twice, you would get the charge conjugation. I will talk about the subtlety in the global points later, but so far let's just take this for the more elementary Z4 action that act on the local fields. So the question that we try to formulate is that, does it make sense to consider a codimension 2 twist defect around which the electric field and the magnetic field are switched? But before that, okay, we have to figure out how the electromagnetic duality is defined as a symmetry defect in the Maxwell theory. This has been worked out by many collaborators. One of them is in the audience. So by looking at the theory, by looking at the Maxwell theory and a with intercoupling E and its electromagnetic dual, which is dual coupling 2 pi over E, a more modern perspective is that you can actually construct a topological interface between these two theories. The construction goes as follows. You can consider the two different theories, defined on the half spaces with a Newman boundary condition on their boundaries. And you can create an interface by coupling the gauge field from the left-hand side, which I denoted as A minus, and the gauge field from the right-hand side, which I denoted as A plus, via a Chern-Simons coupling. You can verify that indeed this topological interface action is going to give you a continuous stress and tensor across the defect. So in that sense, that is indeed a topological one. And it's going to give you this identification between operators as I listed here. Now, more recently, people realized that this is not the only way that you can construct topological interfaces between gauge series with different gauge coupling. Another way is by this trick of discrete gauging, such that you can construct a topological interface between two series whose gauge coupling differ by a ratio of a rational number. And here we consider the example where we construct the first topological interface between the series with gauge coupling E and this electromagnetic dual, whose gauge coupling is 2 pi over E. And then we consider the second interface between 2 pi over E and the third phase that is differed by 2 pi over E with a factor of n, which is an integer number. Now it happens that if the gauge coupling satisfies the condition that E squared equals to 2 pi n, they can be identified as the same series. And then you can fuse those two topological interfaces and end up with one codimension one symmetry topological defect in your original series. And that's how this defect is constructed. And more importantly, if you work out path integral by fusing these two symmetry defects together, you would have found very surprisingly that their fusion rule is no longer group-like, and that is lead to this non-invertible symmetry. Okay, now we are one step closer to define what does this twist defect means. One major difference here is that now this symmetry defect looks like some PQFT operator that has some interesting gapped both degrees of freedom. Now it is a well-known fact if you are working with 2 plus 1D TQFT that these TQFTs always lead to some interesting massless H mode. So a very first concern that we had in mind is that, okay, since this TQFT could possibly lead to some massless H mode, do we have to consider the possible coupling, for example, between this H mode and the bulk field? That it may even make sense to consider such couplings. Well, nevertheless, let's just pretend that let's just shut up and do the calculation and see how it goes. So this defect, the presence of the codimension 2 defect for sure breaks the Lorentz symmetry as well as the conformal symmetry of the 3 plus 1D spacetime. And it leads to a residue conformal group whose weight are characterized by H and H bar as you are doing in the 2D CFT, with a transversal rotation group characterized by the quantum number spin S. I apologize for running out of notations. And at the classical level, this symmetry defect would lead to a modified equation of motion, which lead to the twist condition such that every time you wind around this defect, the field strength of your Maxwell series F is mapped to the its dual, which is star F, and that leads to the order 4 spin selection rule, such that the spin has either to be integer plus or minus 1/4. Okay, so these are the two symmetries we had at our hand. It turns out these two symmetries are so strong that it completely fixes the possible defect degrees of freedom, and it eliminates the possibility that the H mode could couple to any bulk fields by any way. So let's explain how that is possibly done. We show this by starting the possible structures in the bulk 2 point. So in the bulk 2 defect 2-point function and the possible structure in the bulk 2 defect 3-point function. And we're going to show that this twist defect that actually allows a universal rigid and chiral by rigid, sorry, I should say, okay, it will become obvious momentarily. It admits a rigid and a chiral and a generalized 3 series vector that is going to completely decouple from whatever degrees of freedom that is induced by the presence of TQFT. Okay, so how that is done? Right, we first consider the possible bulk to defect two-point function. And the thing is that conformal symmetry is so strong that the possible form of the two-point function is completely fixed up to an overall coefficient, which is the OPE coefficient. And now, by requiring that the bulk field strength has to be closed, we can solve this equation and find out that to admit a non-zero two-point function between a bulk field operator, and a defect primary, the only possible scaling dimensions, the only possible conformal weight of the defect primary has to be that they satisfy these two conditions. So they can either be a vector with parallel spin L equal to 1 and the defect dimension 1 plus the absolute value of S, or as I showed here, with the defect spin S equals to -1, and with the spin taking the other values. So the take is that the only possible defect primaries that can sustain a non-zero two-point function with a bulk strength has to be this set of chiral vectors.
Well, what about operators in the bulk that don't obey an equation of motion, like F squared, for instance?
Right. In that case, you can consider this OP channel. You can first fuse the two operators in the bulk field first, and then consider taking it close to the defect into the OPE. And this procedure has to commute with a case where you do the OPE for the two operators individually, and then take the set of bulk operators, take the two defect operators together. I need to draw the diagram if you have it in mind.
The key thing here is that since the bulk is free and its operators are being generated by F, so this is sufficient.
Yes, exactly. Right. Okay. Now that's for the two-point function. So the two-point function told us the possible primaries that has a non-trivial two-point function has to be those chiral vectors. Note that the spectrum of these vectors are asymmetric on their fraction that exchange H and H bar. So the spectrum is chiral. Now, what happens for the three-point function? Starting from the 3-point, now you can start to build a conformal cross ratio with 3 different coordinates. And similarly, the function form of the 3-point function are completely fixed up to the coefficient as a function of the cross ratio. So, quote unquote, they are the OPE functions of Kc, where the Kc is this very complicated combination. And now let's play the same trick once again. By requiring that the bulk field strength has to be closed, we would have found a set of OPE coefficients. We would find a set of ordinary differential equations for those OPE coefficients as a function of Kc. And if by requiring the solutions to that Kc has to satisfy certain conditions as required by unitarity and some well-definedness in certain limit, we will see that not all solutions are possible, first of all. And for those allowed solutions, the quantum number of those defect operators has to satisfy certain condition. And this condition is indicating that the defect primaries are generating a generalized free series vector of the defect. In the sense that whenever you fuse the B operator, the chiral defect vector primaries, with an arbitrary defect operator, on the right-hand side of your OPE equation, the primary dimension has to satisfy that there exists no anomalous dimension. This is an extremely strong constraint, and it leads to the consequence that the multiple correlation function of this defect primary V has to satisfy the weak theorem. And by that standard, we call this is a generalized free series sector. Okay, so far, is there any questions so far? Okay, I realize I probably is discussing many abstract and the size of DCFT, but I want to convince you that they are actually physical. Now, by the state operator correspondence, you can actually map those defect operators to some states. In this case, the states in the S3 sphere, with the twist defect occupying some large circles of the S3. And this is in particular this coordinate of S3 with the state operator correspondence mapping the quantum numbers of our operators to the energy, to the Fourier wave number, and the spin with respect to different coordinates. And you can find that indeed the chiral primaries of your DCFT that is generalized free describe certain wave profiles in which I'm showing you the Poynting vector, the flow of the energy flux in space in a slice of S3. And what we found previously lead to some physical meaning. So first of all, this generalized free series sector is chiral. That means the phonon waves in this S3 Hilbert space has, in the terminology of the optics, has the behavior of the spin momentum log, in the sense that the momentum along the defect are associated with a spin transversal to it, which is a characteristic feature of the chiral equivalent in quantum optics. And the second, these phonons has to decouple from whatever local degrees of freedom you had on the twist defect. That's a strong constraint from the two simple conditions that we started with. That is, first, we are looking at a conformally invariant twist defect, and the second, this twist defect is associated with is attached to a symmetry defect that implements electromagnetic duality. So that's a really non-trivial consequence. Now, as I said, if you consider this symmetry defect as some 3D DQFT, you would probably expecting some massless age mode due to this DQFT. And that is indeed the case. If you consider the anomaly inflow, that you would have to end up with the conclusion that there exists a decoupled sector. Well, I should explain more. Since the generalized free series sector does not absorb the anomaly inflow of the gauge transformation of the symmetry defect, you would expect there exists a decoupled chiral current sector, which is effectively described by a chiral compatible boson. And you can verify that the chiral compatible boson, the quantization of the chiral charges, are determined by insertions of certain topological defects that the links with a twist defect in space. And in that sense, that is indeed the generalization of the anion line in the consignments, such that it decouples from the bulk from the local perspective, but it only has received correction from both from some topologically non-trivial configurations of the one-fold symmetry operator. Okay, I think that concludes my discussion here. So I want to make a very short, or maybe too overwhelmed, summarize of my topics today. So in the first part, I showed you one possible applications and why experimental people should care about twist defect. There is the correct IR model for certain lattice imperfections that we encounter every day. And for the twist defect in the free Dirac fermion, it has two different defective points. And at a certain point where these two fixed points come across, it leads to the important experimental implication, such that the final size effect is going to get larger and larger, and eventually make your numerical simulations break down. Now, in the second part, I talk about the twist defect in a gauge theory, in the simply possible gauge theory, that is the U1 Maxwell. And the take-home message is that the twist defect contains a universal and chiral and a generalized free series sector as a consequence of the conformal symmetry and the non-trivial symmetry transformation induced by the symmetry defect attached to it. And that is a unique answer we can ever get. And this sector is going to decouple with whatever local degrees of freedom that lives on the 2D twist defect. Okay, I shall end up with some open questions. But before that, is there any question about the main topic today?
Can you go back to the Maxwell discussion? So
yeah,
where does N show up in this sector? Does N matter? The coupling V, does it matter here?
The exercise shows that N cannot by any means enter can be any means manifested in the free series sector. There will be coefficient, the dimension. Everything about the generalized free series sector has to be completely independent of capital N.
But does that mean that this sector that you're finding could be interpreted as some defects sector that exists at general coupling?
Yeah, true. But in that case, we don't know how to define the symmetry defect in itself. The global coupling only enters the spectrum or any other dynamical properties of twist defect via a decoupled chiral current sector. Sorry, where is this slide? Right, it only when you consider something that is completely decoupled from the both degrees of freedom, and that's where the global properties of N enters into consideration. So the chiral compact boson as an effective model has the radius equals r squared equals to N, and the spectrum is manifestly dependent on N.
And the other sector, the generalized free field sector, can you describe it through some fields and equations of motion?
Fields equation, bit confused.
Well, I mean, you said it's generalized free fields. Is it the free fields of based on some Lagrangian that we could say?
First of all, from a 2D perspective, it is non-local.
It's non-local.
Right. You cannot write down a localized 2D action that effectively produces spectrum. Well, first of all,
why was that?
Because there is no stress in the tensor.
No, okay, but
Okay.
I meant like I guess a 4D, 2D bulk coupled system.
Well, that I'm not sure. The thing is that if you remove one of the constraint, if you remove the twist condition, and you only consider some surface defect in your Maxwell theory, there is possibility that you end up with an interacting DCFT. And I'm not sure if in certain cases you happens to end up with the same spectrum. I cannot exclude that possibility. But for this specific example where the twist defect is associated with a 3D symmetry defect, I think there's only one unique answer as a consequence of it requiring those two conditions at the same time. Okay. Okay. Do I have how many time do I have?
You have about 4 minutes. You have time to do your question.
Okay, good. Right. Okay, since I got another 5 minutes, let me just quickly comment on the open question that we have learned from this twist effect, in the Maxwell theory. So one interesting question to ask is that since we end up with a chiral spectrum, remember that the operators in the generalized free series sector are asymmetric on the reflections that exchange H and H bar. How do we measure the chilarity of the twist defect? Is there a physical way that we can define our measurement? We come up with this proposal that maybe one possible way is to place this twist defect on a compact Hilbert space, which is S3, and placing the twist defect along a great circle of S3. In that case, you can calculate the Casimir momentum induced by the presence of twist defect equals to 1/16. Sorry, 1/16(4). And we conjecture, the proof is still in work, we conjecture that this quantity measures the gravitational anomaly, the chiral anomaly of the twist defect, which equals to 3/8. Well, another possible directions of this twist defect that we can consider is analog in more complicated models. For example, the n equal to 4 super EMFs. In that case, if we want the twist defect to preserve the supersymmetry as well, so that they are BPS, we inevitably have to consider some curved space background due to the fact that the supercharge also picks up the phase under the electromagnetic duality transformation. And therefore, the twist defect would break the supersymmetry. To compensate for this extra phase, the only thing we can do is to turn on a non-trivial background for the R symmetry. And since the R current is at the same supermultiplet of the strengthening tensor, we inevitably have to consider a curved space background for this duality transformation, which I found is a fun effect. Okay, that's the two questions that we're considering right now. And I think I should conclude in this slide.
I mean, your pinnacle for twist defect should have had a string theory realization already as a 7-brane or something.
Yeah. That could be. But as I say, here the situation is a little bit more involved, since now you have to consider a conical singularity as the location of the twist defect.
Well, I think that would happen automatically because the 7-brane, the back reaction of the 7-brane is strong. It actually makes the defect the metric conically singular around this. So it's, yeah, because it's codimension 2 in space-time in string theory, you can't ignore the back reaction, so the conical singularity.
I see. Okay.
It actually fits very nicely.
Well, I should mention that if the space-time is conical, this DCFT exercise would have to be tweaked at slightly bit. And it could be that with a certain conical angle that you end up with not the unique DCFT, not the unique generalized free series sector that I'm showing you this slide. It could possibly allow another fixed point with a certain conical background. So yeah, I think that's something interesting. It could, if I'm being ambitious, I would say maybe for the superunion Mills, it allows more than one possible fixed point than I just showed you in the free Maxwell. Maybe the structure is more complicated in both. Any other question?
Yeah, so you mentioned several times that experimentalist should care about the Marjorie size. An experimentalist that has a lattice like you have would also have phonons, which would interact with defect. Is there, are your predictions robust against these other gapless excitations that are
Right. Well, it could be that you end up with, in the IR series, some massless bosonic without freedom, in addition to the fermionic sector. And more generally, you can end up with some interacting CFT. And it turns out that for this defect conformal manifold, all I can say that for sure it does not exist in 3D QED. If you turn on some effective gauge photons from the lattice, then this conformal manifold would cease to exist anymore. And that has been worked out by some other collaborators, some other authors, Brandon, Adolf, and Zohar. And they tried to work out the analog of this twist defect, but now in QED. In that case, I think their conclusion is that it's due to the spin imperity in the O4 model.
You're talking about 2 plus 1D.
Yeah, 2 plus 1D. Yeah, this is about 2 plus 1D. Yes, sorry. So, okay, so the short answer is, if you have some bosonic distribution freedom, yes, this picture could be dramatically changed. And you probably don't find a similar manifold anymore.
So I think you answered this in response to Gabriel's question.
Yeah.
But can I just ask again, if you there's no obvious picture about what you should do in the lattice theory to get to alpha equals 1/2.
So sorry, say it again.
I mean, to approach the point with the conformal manifold.
Yeah.
What UV parameters you should be tuning in your lattice model?
Well, first of all, those topological quantum numbers are robust against any local modification. Let's say I change the coupling slightly here. That is not going to change the topological quantum numbers. They are robust to the local perturbations. And the second, for the total flux to approach 1/2, for example, all you have to do is just find a suitable set of numbers with this combination here determined by the rotation that implements the lattice disclination and the momentum of Dirac horn, the sum of which add up to 1/2. So that could be a physical scenario where the simulation and the simulation breaks down and you have to care about some large finite size effect. Did I answer your question? Yeah. Okay, let me answer again.
Maybe the question is more like, how, suppose you want to make the system with alpha equals 1/2. What do you do? Could you tell us a lattice model that?
Right, so one practical way, if you are so unlucky that your imperfection gives you 1/2 flux, one practical way to play with this the fixed point is that you can act on top of the imperfections on external flux, and you can dial with external flux, and find some point that is far away from the defect fixed point, conformal manifold, as we did here. So here we also try to identify this shift, this horizontal shift caused by these topological quantum numbers, and our strategy is not to look at one point only, as we always have the risk that the total flux is close or equal to 1/2. So we did is that we scan all different values of the external flux from 0 to 1 and draw this diagram, and then identify the shift horizontally of the topological quantum numbers. So if you are an experimentalist and you want to be sure that you are not working in the dangerous area, I would suggest that you add some external flux, external localized magnetic field strength added to lattice imperfection.
So just let me see if I understood more or less correctly. If you go back to your lattice,
Yes.
you either remove some angle, like in one side you remove 90 angles, the other side you add, I don't know, 75 degrees.
Yeah, that is case for the disclination.
Yeah.
It's very similar to the dislocation, where you remove one arrow of the atoms. And for disclination, what you essentially did is just to pick up an angle and cut everything out and glue it back together.
And but when you do this is gonna give you one alpha, but besides this, you have a magnetic flux, and this is gonna tune you on which specific point you are. So it's a combination of the magnetic flux plus the
Plus
excess
some
angle.
conical background. Here I'm only showing you the case where there's no conical singularity. So this, I should emphasize that this phase diagram, this defect spinor dimensions are for the case where there's no conical singularity. For the case there is, I shall refer to you to our paper where we work out these more general cases and the corresponding result. The curves are going to be slightly more complicated than this flat space case, but the phase diagram is roughly speaking the same. And there's also a crossover of fixed point leading to the exact defect conformal manifold. Okay.
Okay, if there are no more questions, let's thank the speaker again. I assume you're all dinnered out.